Good evening, everyone. This is SMC 1999, question number 25. This question, even though I'd done it once before, still took me under a little, I think probably a little bit underneath an hour to solve, maybe even just a bit over an hour to solve on a second attempt. So it had been a while, because I didn't remember the answer. Okay, but trying to solve this problem from scratch for me was very difficult, and probably because I'm not really used to seeing these type of problems in SMC. You don't really get these sort of infinite series questions in an SMC paper. They are, I think actually this question was, when I first put this question on my live, I think it was Charlie who told me that this was once a step question. There was a step question that was similar to this and gave you this sort of series and with some other cool stuff and asked you to do some stuff with it. And so he told me that, and so, you know, I think it's not unfair to say that this is more sort of like something that you would expect to see maybe in a step problem with extra parts and a little bit more to it, right? As opposed to an SMC question. But as an SMC question, obviously, you would expect, therefore, that there is a solution without necessarily going into too much series notation, etc. And there is, which effectively is a solution that I found. But it's a lot more elegant when you do write it with series notation. So yeah, just keep that in mind as I go through this, because the way that I found it is just by sort of noticing some patterns, which is kind of really the only thing that you can do. And I don't remember what their solution was, but I believe that that's what they expect you to do as well. Is they expect you to just sort of do some stuff with this and find a pattern. Okay, so effectively what you want on the right, so you want obviously what we know is that if we could call this sum S, right? So S is just this sum, right, or the value, the output of this sum, right? Which is just like, yeah, what you get when you add all this stuff together, okay? And obviously what you're looking for is, on this right-hand side, you're looking for like some constant plus like S over whatever, for example. Like often what you can do with infinite series, you can rearrange this side to get effectively like some constant plus maybe, you know, PS, right? Don't know why that's not showing on the computer. So why is that not showing on the computer? It's my internet character, there we go. Honey, hey, what are you doing? Hey, you cheeky. Sorry, my cat's here. But effectively, the aim of the game with these sorts of infinite series problems, is effectively to get the right-hand side in this form, where you have like some constant k, okay, which is effectively, you know, which needs to be determined, plus some scalar p multiplied by s, which is just our sum, okay. I mean, it will become more clear what I mean as we move throughout this problem, okay. And p actually doesn't necessarily, I mean, neither k or p need to be integers. Actually, they could be fractions. In this case, they will be rational numbers, but I don't think they necessarily need to be rational numbers either. Okay, but effectively, if we can get sort of this type of format, right, where the sum s is equal to a constant k plus p times capital S, then we can easily solve for s by just rearranging that, right? So you just get s minus ps is equal to k, s multiplied by 1 minus p is equal to k, and so therefore you get that the sum s is equal to k over 1 minus p, where k and p are constants to be determined. Okay. So in general, if we can do that, then we're done effectively. But the question really is then, how do we do that with this? And that's sort of something that just takes experimentation. Because one of my ideas initially was effectively just to basically just take 1. So obviously, by the way, if you haven't already realized what this sum is, so it's actually, in sort of sigma notation, the sum of f sub n over 2 to the n. Basically n for n greater than or equal to 1. So from n equals 1, this just means from n equals 1 to infinity effectively, okay? So this is just the same as the sum from n equals 1 to infinity of f sub n over 2 to the n, okay? Now f sub n is the Fibonacci number, okay? So Fibonacci numbers obviously are obtained by starting with 1 and 1, and then adding the previous, effectively, 2 terms to get the next term, right? So effectively, if I add these 2 terms, I'm going to get 2, then I do 2, and then I effectively add these 2 terms to get 3. So effectively, if you add the previous 2 terms from where you're currently at, you'll get the next term. So effectively, I think if you write it out, you'll have fn is equal to fn minus 1 add fn minus 2, and this will obviously hold for n greater than or equal to 3, I want to say. So because obviously you have f1 equals f2 equals 1, so those are the first 2 terms of your Fibonacci sequence, and that's just the way that we've started it, right? So that's like the rule that we've given, and then obviously for all n greater than or equal to 3, we can obtain them by adding the previous 2 terms. So for f3, it's going to be f1 plus f2, f1 plus f2, which is obviously going to be 2, and f4 is going to be equal to f2 plus f3, which is just 1 plus 2, which is 3, okay? And then you just keep doing this process. So f5 is 2 plus 3, then 3 plus 5, 5 plus 8. Okay, so those are the numbers on the numerator. They're just Fibonacci numbers. Okay, and obviously the index of our sum tells us which Fibonacci number is on the numerator. And then on the denominator, we just have powers of 2. So 2 to the n, right? That should be fairly obvious. I guess Fibonacci one might be a little bit unclear, though, just from looking at it. But Yeah, I mean, there you go, right? That's actually what's happening, but we need to evaluate this. And the reason why this is so annoying is because of the Fn here. There's no clean form, really, for those numbers. Obviously, they do link to things like the golden ratio, etc. But ultimately, though, you don't need to know any of that for this. I mean, it will probably help, but I certainly don't need it. So I guess the question is then, how do we get this into, obviously, our form and evaluate it, right? So yeah, I mean, like I was saying before, like I was about to say, my first idea was just to basically just plug everything together. So take out ones from the numerator bit by bit. So what I mean by that is obviously this sum is just a half, plus a quarter, plus an eighth, plus a 16th, plus 1 over 32. Because I know how to evaluate these sums, right? Because this is just geometric in nature. So I know how to evaluate this, right? I know that this will sum to 1, okay? Because effectively for a geometric series, you know that A, so the sum to infinity, right, of a geometric series, S infinity, if it converges, which is given here, it will be given for this entire question, because effectively the thing that we're multiplying each term by to get to the next term, the modulus of that is less than 1. So, yeah, I mean, really I should write these things down, because that might be confusing for people who are not familiar with geometric series stuff, but if you're not, I'd highly recommend that you do get used to that, because it's quite common. I wouldn't say in SMC, but I would say in general, just a nice thing to know. So geometric series, obviously, okay, so for a geometric series, the sum to infinity is equal to a divided by 1 minus r, only if the modulus of r is less than 1. So remember that for a geometric series, we have a starting term, in this case a half, then you have a scalar that you multiply this starting term by to get to the next term. So in this case, it's a half, so that's our value of r. So you multiply this by a half to get to a quarter, that by a half to get to an eighth, that by a half to get to 16th, so on and so forth. So you multiply each term by a half to get to the next, right? So that's the value of r. So r here is equal to a half, and a is equal to a half as well, okay? And so we can prove, although I won't do it here, that the sum to infinity of a geometric series is a divided by 1 minus r, only if the modulus of r is less than 1. And the reason for that is because if it was greater than or equal to 1, then the terms get bigger and bigger. So when you add them together, you obviously get a diverging series, right? You get basically infinity. Okay, so obviously though, for this entire question, you can use this rule. You won't need to worry about the semantics. That's not really the point of the SMC, to be honest. The point is just to have some interesting questions. So in this case, we have a half divided by 1 minus a half, which just gives us 1. So we know that the value of this is 1. That's very easy to evaluate, okay? The reason why the initial question is very difficult, though, is because we have numerator that is not just ones, okay? So it's not a constant scale factor that you're multiplying by. So it's not geometric in nature. It's not really arithmetic in nature. Okay, there's no constant difference between the terms. So it's very difficult to, those are the two common ones, right? So it's difficult to ascertain necessarily what the next step is. So I have this idea to make it geometric, because you can force a geometric series out of this. But obviously then what you have to do is you have to take the remaining parts. So that gives you an eighth plus, and then it's going to be 2 16ths, right? So it's going to be, because you've used up one of the 16ths, 2 16ths plus 4 over 32, and so on and so forth. And then you just keep, this is sort of the remaining parts. So it's going to be 1 plus all of this. Okay? That's basically where I started off with. And I mean, now I wonder, let's just keep going down this route, because I never really completed this route. I kind of just went exploring down other routes. But if we have 1 plus an eighth plus 2 16th plus 4 over 32 plus so on and so forth, then we can just continue my idea. We can force a geometric and take the remainder and just keep doing it until we don't have anything left. Okay? And so in this case, obviously, we're going to get 1 plus, in this case, an eighth plus a 16th plus 1 over 32, right? And so on and so forth. Okay, so we're only going to have one of those, okay? And then we're also only going to be able to therefore fit one of the next. If we just keep doing this process, obviously, we can do 1 over this, 1 over 64, and so on and so forth, right? You keep doing that. But you're only going to be able to do this once as well, because if you've used it up now, you only have 2 16ths remaining at this point. You use one up here, so you only have one remaining here, okay? And then after that, you will have only you only have 2 over 32 left. So then at that point, you will also only be able to use one of those. You'll be able to use 2 of those, right? Because you'll have 2 over 32 remaining, so you can do 1 over 32 plus 1 over 64 plus so on and so forth, and then do it again. So then you get this pattern, right? And then after that, how many 64ths are you going to have left? Well, how many did we even start off with? We started off with 8, okay? We've used up 1, 2, 3, 4, 5, 6, 7. So I think we're only going to have 1 left, if I'm thinking correctly. We start off with 5 over 32. Oh, wait, we started off with 30 seconds. That doesn't quite add up then. Hold on, have I been doing this wrong? Oh, no, that's fine. Oh, wait, hold on. Yeah, no, what am I doing? Sorry, I was counting this. I was counting all 5 of the lines here, but actually I'm over-counting some stuff, aren't I? Okay, so what I really mean is that, so obviously here we've used it once, right, to get that. Here we've used it twice, the 64, okay? And then here, but then you don't double count these, okay? So then here we've used it 3 times 4, 5, okay? Then we have 3 remaining times. So we're going to have 3 times 1 over 64 plus 1 over 128 plus 1 over 256 and so on and so forth. Okay, and then you continue this, okay? And then, so we have 3 plus 5 plus 6, 7, then 8, right? So then we've used up 8 of our 1 over 128s, and we're going to have 5 remaining. So you do this, then you have 5, and I can stop the pattern in a second, because I think this actually does end up working, okay? Plus 1 over 512, and so on and so forth, okay? So then you just keep, you keep doing this, right? You keep, so you started here, and you effectively, as you go down, you just keep taking the remaining part and then forming as many geometric tails, if you will, as possible, right? And that just gives you the value of the sum, okay? Now, obviously, for all of these geometric tails, we'll always have r is equal to a half, as you can see, because to get from an 8th to a 16th is a factor of a half of 16th, and that's just ultimately because, remember, the denominator is a factor of 2 to the n, right? So basically, to get from the 1/8 to 16th is multiplying it by a half, 16th to 32nd multiplying it by a half, because the denominator is 1 over 2 to the n, and now the numerator is just all ones. So the fn has just been effectively, like, we managed to distribute the Fibonacci number over the sum. We can, like, lengthen it out such that we're only dealing with unit sort of fractions where the numerator is 1 and the denominator is of the form 2 to the n. And so then all we really care about is effectively the thing that we're multiplying by to get from 2 to the n, 1 over 2 to the n, to 1 over 2 to the n plus 1, which is just a half, right? 2 to the power of n plus 1. Yeah, so that's why r is always going to be a half. And so therefore our sum to infinity, which always exists because r is equal to a half, which is less than 1, is therefore going to be a over a half. So it's always going to be equal to 2a, okay? So we can use this rule to quickly evaluate all of these geometric tails and see what happens, okay? But the other important thing that you're going to notice here is that actually when you have a look at all of these, right, these coefficients actually form the Fibonacci numbers, right? So this 1, 1, 2, 3, 5, and then if I were to continue this process, I'll just get 8, right, 13, right, 21. That is a Fibonacci. These are Fibonacci numbers, right? Yeah, exactly. And you just continue the process on and on, right? And so actually there is some Fibonacci stuff going on here. So maybe when we evaluate the geometric tails, we'll see what's going on. Okay, so effectively we have that 1 out the front, so that just gives us, that thing there is equal to 1 plus, so 1 times 2 times an eighth, right? Because effectively, don't know why that 3 is not, okay, you guys can't see it anyway. So effectively we have this geometric tail here with the 1/8 plus 1/16 via this sort of rule that s infinity is equal to 2a. We know that's just going to be equal to 2 times 1/8 because a is equal to 1/8 there. So then effectively that just becomes 1 plus a quarter, right? And then we use the same method and you see that you get 1 plus a quarter plus an eighth, right? Plus 2 times a 16th, plus 3 times 1 over 32, and then add 5 times 1 over 64, 1 over 64, and then add, so 1, 1, 2, 3, 5, 8, obviously, times 1 over 128, and this pattern will just obviously continue, okay? And if we just look at what this is giving us, we have 1 plus a quarter, plus an eighth, plus 2 sixteenths, plus 3 over 32, plus 5 over 64, plus 8 over 128, and so on and so forth, okay? Now, this is the point when you need to look at this, okay? You need to look at this tail and be like, what actually is this? Like, what is it? What is this? Okay, because this is really crucial, okay? If you don't really see this, then you're kind of lost, right? But if we go back up to what we started off with, what was it? It was a half plus a quarter plus 2 eighths plus 3 sixteenths, okay? All of that. But what happens then? So if that is s, right? If that is our sum s, a half plus a quarter plus so on and so forth, then actually what you notice is that a half s, so s divided by 2, is equal to a quarter plus an eighth plus 2 sixteenths plus 3 over 32 plus 5 over 64 and so on and so forth. And that actually, I believe, okay, that s over 2 is exactly what we have down here, okay? Yeah, a quarter plus an eighth plus 2 sixteenths plus 3 over 32 plus 5 over 64 and so on and so forth, right? So actually we can replace all of this, even with the extra dots and stuff, with just s over 2. That's just equal to 1 plus s over 2. Okay? So this, our entire sum s becomes this, right? So now we have, so what we can say is that so s is equal to 1 plus a half s, right? So we found our constants from before, right? Because we wanted it in the form k plus ps, right? So s is equal to k plus ps. In this case, our k is equal to 1, okay? So actually it wasn't, I thought it was, oh no, because I think I had a slightly different thing before. Maybe that was the reason why. Yeah, I had a slightly different sum, I think, actually. But effectively, in this case, we have that k is equal to 1, and obviously p is equal to a half. Actually, no, I did have the same thing. I just bugged out, my bad. P is equal to a half, okay? So k is equal to 1, p is equal to a half, right? And so then we can just solve this, right? It's fairly simple to solve this. And so what you end up getting is a half s, right, is equal to 1, right? And so s is equal to 2, which is the final answer. So all of that stuff that we're adding up, that entire sort of sum, gets us exactly the value 2, which is the correct answer. Very, very interesting question. Not really a typical SMC one. 1999 obviously was a while ago now, but a very, very, very Fun question, I guess. Interesting question. And it's nice to see that Fibonacci pattern come out, right? I think I really actually that it is a lot nicer if you were to write it in series notation, if I remember correctly. But there we go, right? You can still see the pattern hopefully and see what's going on. And yeah, okay, awesome stuff. See you guys in the next one. Goodbye.